One of the trickier problems that we have to answer using calculus is what's the length of a curve? So if you just have some weird shape out there, how do you measure the length of it? We know how to measure stuff that's straight, you know, using rulers, tape measures, or lasers, or something like that. But how do you measure something that's curvy? There's a lot of practical ways to do it. Like you can put a string across there, lay it really, really close, and then stretch the string out and measure its straight distance. Of course, you can have a lot of error in there because you can have stretchiness, or did you get it perfect? You can take a wheel and roll it along the curve and then measure how many times it went around, figure out the length that way. But how do we do this mathematically? So let's take a look, and I'm just going to structure it like this. If we have some curve, let's here called f of x, and I want to know how long that curve is from A to B. Now, that's fairly straight, but it could be any curve, of course. How do we do this? Well, like a lot of problems we face in math, we don't look at the entire problem at once. We take a look at an infinitely small piece of it. So here's what I'm going to do. Imagine that being a little tiny zoom window. I'm going to start zooming in right there on the graph, and I'm going to zoom in an infinite number of times. Now, it should make sense if you zoom in an infinite number of times, no matter how curvy something is, it's basically straight. So this little piece here, imagine it's an infinitely small little slice out there. We're talking about arc length. By the way, I'm going to use lowercase s for arc length. So that's a very, very, very small piece of the entire length of the curve from A to B. So how do I figure out what that is? Well, think about it like this. If we move that way, I can break that movement down into two directions. A very small piece of movement in the x direction and a very small piece of movement in the y direction. Now, of course, by looking at that, we get ourselves a right triangle, and we know the relationship between these sides. I know that ds squared is equal to dx squared plus dy squared. So right away, I can come up with an expression for what ds is equal to. ds is equal to plus or minus square root of dx squared plus dy squared. Now I can simplify this one even farther because we're talking about the length. And when we measure length, we tend to think of length as a positive quantity so far. So I know I can't have the minus here. So we end up with this basic expression. Now, we're going to see a lot of different expressions for arc length, and they all start from basically right here, this entire idea. Now, from what we do next depends on what type of math that we're talking about. Here's what I'm going to do. If I want to add up all these little pieces of arc length to get the entire arc length, I got to decide, am I going to add them up in an x direction or in a y direction? Kind of that would be this interval here. I'm going to do it in the x direction because that's visually how I kind of have it set up right now. So if I want to add them all up in the x direction, here's what I'm going to do. I'm going to take this, let's say ds is equal to, on the inside, I'm going to factor out dx squared, y squared over x squared, and you would get that expression. You can see just distributed back in here, right back where we are. Now that I have things joined by multiplication, I can do the square root of each one of those. So that'll be the square root of dx squared, square root of 1 plus, now since both of those are squared, I'm going to go ahead and write that as dy dx squared. All right, we're getting close. The square root of dx squared. Now, most of us would make a mistake and say the answer to that is just dx. I'm going to bring it up here. Well, it's not. I'm going to write this piece first. That's actually the absolute value of dx. Remember, anytime you take the square root of something squared, you get the absolute value. Now, I can get rid of that because remember, dx we measured in this direction. And since we're talking about the arc length from A to B, as we move to the right, dx is increasing or is positive, right? The change as we move to the right is going to be positive. So I can get rid of that. So the first expression I end up with is this, 1 plus dy dx squared dx. Now, by having the x out here is kind of saying we're measuring this in the x direction. So I can finish this up. Since this is the small piece of it. All I got to do is add them up. To add things up, we integrate. So if I integrate both sides, 1 plus dy dx squared dx, we would end up with the arc length. So little s again standing for arc length, be integral 1 plus dy dx squared dx. And generally, remember, we want the arc length, if we did the entire function, of course, most of the time it would be infinitely long because it goes on each direction. So we need an interval. We're generally going to talk about the arc length over some interval from A to B. So there's our arc length formula. However, I could have changed things just a little bit way back up at our very first kind of step that we did. I decided we were going to measure this in an x direction. We could have measured this in a y direction. So we could have thought about this as some function of y and measured it in the y direction. The only difference would be, instead of factoring out a dx, we factor out a dy. Same stuff happens, and we would end up with the integral from, let's say, c to d, square root 1 plus dx dy squared dy. So the first one is if we're measuring in an x direction, or basically we have a function of x. The second one is if we're measuring in a y direction, or if we have a function of y. So the good news here is this is just a formula now. You need to know it. You need to know your arc length formulas. That's the good news. The bad news is most of the time these are impossible to do. The actual integral itself is too hard to do, and you have to approximate the solution. Now remember, we have approximation techniques from Calc 1. We could put an infinite number of rectangles under there. Remember, we have the trapezoid method, we have Simpson's method. We had a whole bunch of different methods for approximating the area beneath the curve. So in real life, that's what you'd end up having to do most of the time, is approximate this integral. However, since we're living in a textbook world, most of your homework problems are going to be designed so that you can actually do this integral. Doesn't mean it's going to be easy, but you can actually do it. So let's just try a problem here. Find the arc length. Let's do y is equal to the natural log of the cosine of x from, let's go 0 to pi over 4. All right, so just as I said, most of these aren't going to be able to be done, which means most of them have to be designed to be done. So I'm actually cheating here a little bit. I'm going to steal a couple out of your textbook. So to do this, remember, I'm just using a formula. Since that's y is a function of x, I'm using this one. So I need the derivative of that function. So let's go ahead and write that derivative. So dy dx, or y prime, the derivative of a log is 1 over the argument times the derivative of the argument, which in this case, sine over cosine is just tangent. So if we plug this into our formula, the arc length will be equal, we're going from 0 to pi over 4, square root 1 plus the derivative squared dx. So let's see, we get 0 pi over 4, square root 1 plus tangent squared x dx. All right, if you're just looking at this, you may say, I'm kind of stuck. Remember, the worst thing you do, you cannot take the square root of each one of those. Very, very bad, right? Because they're joined by addition. However, I do have an identity for that. 1 plus tangent squared is secant squared, so I can rewrite that as a single 0 pi over 4 as a single function of secant squared x dx. Now again, same problem we ran into a moment ago. When you take the square root of something squared, you get the absolute value of that. But remember, where are we looking? We're only going from 0 to pi over 4. Well, that's in the first quadrant. Everything's positive in the first quadrant, so I know secant's positive there. So really, I'm just pi over 4. Okay, so we were able to get rid of our absolute value. Now we have to integrate this. The integral of secant is the natural log of the absolute value of the secant of x plus tangent of x, and we need to evaluate that from 0 to pi over 4. All right, so for time's sake for the video, I'm actually going to stop right there. That's the hard part. Now it's just evaluating, right? Top endpoint minus the bottom endpoint. I'm pretty sure this is an example in your book, so if you want to know exactly what the answer is, you go look it up. But I want to get at least one more example in here, and the next one's going to be a little bit longer than this one. Okay, so let's try another example. Let's find the arc length of, let's do y equals x cubed over 6 plus 1 over 2x. And let's go from 1/2 to 2. I think that's what the book. By the way, again, I'm stealing this out of the book. These kind of have to be designed to work. I'm pretty sure it goes from 1/2 to 2. Okay, so again, to do this, we're just using a formula. Since we have y as a function of x, we're going to be using this one. If we had x as a function of y, nothing changes, just you use the second formula. All right, to do this, I need the derivative, so dy dx is going to be, bring down the power, take 1 away from the power. So let's see, the 3 is reduced, so I get x squared over 2 minus 1 over 2x squared. Remember, 1 over 2 dx is really 1/2 x to the negative 1. Bring down the power, take 1 away from the power. All right, so now what do we need to do? We were plugging it into this formula. Now, since this one's quite a bit messier, right? Our derivative's quite a bit messier than our last example. I'm going to do a bunch of work before I put it into the integral because it's going to be messy. So I'm going to figure out all the stuff underneath the radical first. So what is dy dx squared? Well, that would be x squared over 2 minus 1 over 2x squared squared. So x squared over 2 minus 1 over 2x squared. X squared over 2 minus 1 over 2x squared. Let's do a little bit of arithmetic. That's going to be x to the 4th over 4. This times this. What's that going to be? Well, the x squareds are going to cancel. That's going to be negative 1/4. This times this. Same thing's going to happen. That's negative 1/4. That times the last is going to be positive 1 over 4x to the 4th. So I get x to the 4th over 4 minus 1/2 plus 1 over 4x to the 4th. Okay, so that's what dy dx squared is this. X to the 4th over 4 minus 1/2 plus 1 over 4x to the 4th. All right, so far in our formula, I've written out what that piece is. We still need to add 1 to it. So let's get our scratch work out of here. So 1 plus dy dx squared would be 1 plus, what is it? It's x to the 4th over 4 minus 1/2 plus 1 over 4x to the 4th. So this ends up becoming x to the 4th over 4 plus 1/2 plus 1 over 4x to the 4th. Now here's where a couple of things can happen. If you factored out the greatest common factor, you might be able to see this a little bit easier. But I'm going to show you something that's fairly interesting. Watch. I know if I take this and distribute it out, I get this. Now you can see from our scratch work that I just erased. Watch this real quick. If that would have been a plus, the two things in the middle would have been the same sign, so that would have been a plus. Which means, going backwards, this factors to this. So I can rewrite this as x squared over 2 plus 1 over 2x squared squared. So that would have been pretty tricky to see if you weren't paying attention for it, right? Is that once we added 1 to this piece, we basically got the same thing with a plus in the middle. So we know how that factors. Now, the nice thing about that turning into one term, now when I put it inside my formula, this is going to be the integral from 1/2 to 2, the square root x squared over 2 plus 1 over 2x squared squared dx. Now I can simplify this radical. Now again, when you take the square root of something squared, we get the absolute value. So this is the integral from 1/2 to 2. Absolute value of x squared over 2 plus 1 over 2x squared dx. Let's go ahead and move it over here, finish this up. Now, how can I get rid of the absolute value? Sometimes you can't. Sometimes you got to break apart the region depending on the absolute value. But here we have something positive squared plus something positive and squared. So this is always positive. So I actually don't need the absolute value. So this is from 1/2 to 2. X squared over 2 plus 1 over 2x squared dx. So to integrate this, let's just go ahead and write this as 1/2 x squared plus 1/2 x to the negative 2 dx. Now it's very straightforward. It's just a power rule. Add 1 to the power, divide by the power. So the arc length is going to be, add 1 to the power, divide by the power. So it's going to be 1/6 x to the third minus, add 1 to the power is going to give me -1, divide by that, 1/2 x to the -1. And we got to evaluate that from 1/2 to 2. All right, again, I'm going to stop here for the arithmetic for the time's sake. I'm pretty sure, again, this is another example in your book. It may not actually go from 1/2 to 2, so you may want to do the problem with whatever bounds the book has. I think that's the bounds. Plug in your stuff, do a whole bunch of arithmetic, and see if you can come up with the arc length for this. So, arc length, good news, it's just a formula. It's a pretty easy formula at that. Bad news, the integration that you have to do for them is exceptionally hard to do. In fact, most of the time it has to be designed to work, kind of like this. So in the real world, you will have to use some type of approximation method to come up with, well, an approximation of the arc length.